remember where we were? We're talking about triple integrals, right? Six. Triple integrals. And what we said was that triple integrals could be changed into iterated single integrals. So that's the one. Triple integrals can be if they're on the right sort of domain, right? Can be changed into, can be evaluated as iterated single integrals. Iterated single integrals, and just as it was done in the case of double integrals, and as you imagine, this can be done in any dimension. Okay, so the game, so the difficulty is only that how to realize, how to express, say, the domain as a simple region. Right? Where the simple region was something like, your set is going to be x, y, z, R3, where x ranged between two values, a and b. Y ranged between values that were dependent on x, and z ranged between two values that were dependent on x and y. The changing of the domain to this, recognizing the domain as something expressible in the simple form is the only thing that you're not familiar with. And once you have it here, then it's just three single integrals, and you know how to do that. Okay. So the only thing that you need to get some practice in is that's recognizing the domain, expressing the domain as a simple region. Okay. So we were starting last time with this example. W is the solid tetrahedron between x plus y plus z equals 1, the plane x plus y plus z equals 1, and the coordinate planes. Okay. And so here's x, y, z. And you have this tetrahedron trapped in the corner here, right? The corner here between this plane and the origin. Right? These 4 points are the corners of your tetrahedron, right? And you'd like to express that as a simple region. So let's just try it. Let's express this. Express W as a simple region. So maybe try it. Take 1 minute and just like start up how you think you ought to do it. And we'll see. turn to somebody next to you? Or should we turn to somebody that you don't normally talk to? Turn to somebody behind you, say.
There's two variables. I was thinking about trying to just y into just
Yeah, I thought maybe like if X range was really long, figure it out that way. Is this one? Yes. I think so. I feel like that's right. I thought it was
between 0 y plus c follows.
I don't think any of it is
Okay.
Well, the last one's 0 to 1.
Okay. Would anybody like to say what how what they're thinking? Would anyone like to say what they're thinking? Yeah, Flo.
X goes from 0 to 1.
Okay, so x goes from 0 to 1, right? Okay.
And then y definitely goes from 0 to possibly, I think it's x minus 1. I'm not sure. It might just be x.
So
Like,
let's see, right,
trying to visualize.
Sure, right. So remember what the first two things describe, right? The first two things describe the shadow of the object, basically.
Yeah.
Right, the shadow of the object. In this case, the shadow of the object is actually just this bottom piece here, this bottom face. Okay. So x goes from 0 to 1, and then for each x, the y's go from 0 to something, right? Well, how do we figure out that something, right? What's this line here? What's this line? What? Minus y equals minus x plus 1, right? So here we have x plus y plus z equals 1, right? So when z is 0, you get this line, right? When z is 0, you get x plus y equals 1. Y is going to be negative x plus 1 minus x. So y ranges from 0 up to 1 minus x. Okay, right. So that's good. That describes, that gives us the base as an x simple region, right? And then all you have to do is describe z. Right? What's z?
Z goes from 0 to 1 minus x minus y.
Exactly. 1 minus x minus y. Right? Because the plane here is described by x plus y plus z equals 1, and so z is going to be 1, right? The height, z, is going to range from 0 up to 1 minus x minus y. Okay. What if you didn't like to do it that way, but you rather wanted to project it onto the yz plane first? You took your shadow this way. Okay. Then we'll take 1 minute and write down what that'll be. At this point, it should be pretty straightforward. Okay. Project onto the yz, and you can either go make it a z simple shadow or a y simple shadow, whatever you prefer. Okay, would somebody like to somebody like to say what they got? Laura, would you like to try?
Could y go from 0 to 1?
Sure. Yeah, y can also go from 0 to 1. Right? Y goes from 0 to 1, and if you know the y, then the z's range from what to what? 0 to 1 minus y. Do you see why it's 1 minus y? Because this, right, we're describing this thing here, right? If we fix the y, the z's range from 0 up to something that depends on y, right? This line here is x is 0, so we get y plus z equals 1. So what's the z at this height? This is going to be 1 minus y. Right? As you get close, when y equals 1, it goes from 0 to 0. When y equals 0, it goes from 0 to 1. Right? Okay, and then the x's are going to go from 0 to 1 minus y minus c. Right? So that would be your description. That's your description. And then if whatever function you're given, right? Somebody says integrate some function on dv, then you would just set it up whichever way you like. Suppose we use the second one. We're doing y goes from 0 to 1, z goes from 0 to 1 minus y, and x goes from 0 to 1 minus y minus c, f of x minus z, whatever that function is. Okay. So once you have the expression, then it's easy. You just set it up and then do your 3 integrals. Any questions? Let's do a couple more examples, and that'll be it. Let's do this one. So volume. So E is the solid. E is the domain. Below z equals 4 minus x squared minus y squared. And above x squared plus y squared plus z squared equals 4. And I think they mean the lower half of it. So it was, sorry, let me give you the picture. Above the lower half. Right. So the upper guy you see is a circular parabola going downwards, and the lower guy is a sphere. The lower guy is a sphere, right? And you want to express this thing as whatever kind of region. So again, take a minute and express it. As a simple region. Okay, turn to somebody else. Somebody behind you again? Sorry.
So we know from the bottom one. The previous.
That's correct. Because I had it
Oh, it
before.
forms on the-
And then I had y times negative square root 4 minus
All the
square root of
ratios.
4. Yeah. That sounds good.
That's what we do that way.
And then the square root of 4 minus x squared minus y squared. And then 4 minus x squared minus y squared.
Yeah, I did it from the C after and then
Okay,
Yeah.
okay.
I got.
What did you
Go
guys,
from the same
I
thing.
agree with you.
what did you all try?
Right, so we're
What did you, yeah, Laura?
I just have a question, like,
Yes.
how do you know which Z to solve? Like, if you were using it, like, in its domain, like, Z would go from 0 to, say, whatever, but do you use the 4 minus x squared minus y squared, or do you solve for Z in the lower half of the sphere?
Well, so it sounds like you're gonna take the shadow onto like the YZ plane. Is that what you're doing?
Well, it would just be.
Suppose you were. Okay,
Okay.
suppose you do take the shadow on the YZ plane and you want to express it as a Z, express that shadow, right? So here's the YZ plane, you have this thing, and then you have this thing, right? So YZ, and you'd like to express this thing as a Z simple region, although it doesn't look like. I suppose you wanted to start off with Z for some reason. Okay. Right. So what's Z gonna range between? Right. This bottom thing here, x is 0. Right. So this thing is y squared plus the bottom half here is y squared plus z squared equals 4. Right. And the top half of this thing is going to be x is 0, so z equals 4 minus y squared. Right? So, at the top, z is equal to 4, right? And at the bottom, z equals minus 2. Right? So that's how you figure it. Right? Although you see that if we did try to express this thing from here to here, then oh, it's okay. Oh no, it's not okay. Right? Right? We'd have to split it into two parts. Right? We'd have to go from z going from -2 to 0, and then from 0 to 4 to express this as two z simple regions. Right? So that's sort of it's kind of complicated. But if you wanted to, that's what you would do. Okay. So from what I just said, you can probably guess that the projection that you want to take is onto the xy axis, right? So let's take the shadow on the xy axis, right? And what do you get? If you take this thing and look at its projection onto the xy axis, what kind of shadow do you get? You get a circle, right? So how do you express that circle? What is that circle?
X squared plus y squared equals 4.
X squared plus y squared equals 4, and so you can express it however you like, right? X goes from -2 to 2, y goes from square root of 4 minus x squared, negative 4 minus square root of 4 minus x squared to positive square root of 4 minus x squared. And maybe I should have done it the other way, just to Okay, so then what's the range of z for fixed, right? So we've just expressed, what we've done is we looked at the shadow and we said, okay, y ranges from -2 to +2, and for fixed y, the x's range from negative square root of 4 minus y squared, right? That's this thing here, right? Negative square root of 4 minus y squared to positive square root of 4 minus y squared, right? So that's the shadow here. And then for each point in the shadow, xy, right, what's the range of z? Well, you have some point down here, and you have some point up here, right? Depending on where you are on the shadow, your ranges of z are going to be different, right? It'll go from, what's this height? What's the z for this point? Negative square root 4 minus x squared minus y squared, right? And then the upper guy is going to be, it's actually given to you, 4 minus x squared minus y squared. So, negative square root 4 minus x squared minus y squared. Okay. Any questions about that one? Okay, last one. So, last one, you have this object, x, y, z, obtained by taking a circular paraboloid, so z equals x squared plus y squared, and chopping it off at 2 different heights. So you chop that off at a certain height, and you chop it off at another height. Okay. So the first height is 2, right? So this height is z equals 2, and this height is z equals 8. Okay. So you chop that off, you end up with just this piece here. Okay. I'd like you to express this as some region, as a simple region. Let's call this E again. E as a simple region. Okay, turn to somebody else and talk.
Oh, that's so good. Maybe you're right. So, since I made it Z simple again, so I have 8, and then x is squared, or negative square root of x squared, wait, 100. Because if you're like projecting it on the zx, then you say y is equal to 0, so z equals x squared. So it's just negative square root of x squared. And then y is x squared. Cool.
Okay. Okay. So, how did people project? What projection did you take? Did you go on to the xy plane, take the shadow there? No, right? Because I mean, it wouldn't be that bad, but you wouldn't be able to express it as a simple region, right? Because if you took the shadow here, you'd say, okay, I can describe this thing. That's easy. It's a circle, right? You describe it as a circle, and then for each xy, you're going to go from this thing to 8. But then between here and here, you're going to go from 2 to 8. right? So you'd have to express it as two simple regions, right? That would actually not be so bad, because then you have the calculation for a cylinder, which is easy, and then you'd have this thing out here, right? So maybe that's not so bad. But to express it as a single simple region, you don't project onto xy, but rather onto yz or onto xz. So which one did you do?
XC.
Xz? Okay. So take the projection onto xz, right? So your thing is going to look like this: x, z, right? Chopped up at height 2 and at height 8, right? And y is 0, right? So you get z equals x squared, right? So you have this parabola, nice parabola going up, right? And this thing is the projection onto the xz or the yz, if you prefer to call this. It looks sort of like a y anyway. It's appropriately ambiguous. Okay. So, and then what do? You want to express this as a something simple region. Well, it's not going to be an x simple region unless we want to run into the same triple, right? So we're going to make it a z simple region. Right? So z goes from 2 to 8, right? And then x goes from where to where?
Negative square root of z square root of z.
Right, negative square root of z to square root of z. Right. And then once for each xz, right? If xz is fixed, then what's the range of y? What's the range of y?
Negative square root of z minus x squared.
Mm-hmm. Right. See, right? If you x and z are fixed, right? This thing is described by this, right? So we know that y squared is x squared. I'm saying z minus x squared. Right? So y is plus or minus the square root of z minus x squared. Right? So y's range then is going to be from negative square root of z minus x squared to positive square root of z minus x squared. And then as usual, you set up your integral. Your integral will be dz dx dy, going from 2 to 8, from negative root z, positive root z, from negative root z minus x squared, positive root z minus x squared, whatever the function is. Okay. So easy. I hope you're getting the hang of expressing these things. Not so bad. Any questions? Okay, let's go on. Okay, so just like what we did for double integrals, we can do changes of coordinates, change of variables to simplify triple integrals, just as we use polar coordinates to simplify double integrals. We can use some sort of an analog of polar coordinates for triple integrals. Okay. So 16.7 and 16.8 are on two different coordinate systems, cylindrical and spherical coordinates. We'll probably only do the first part. Okay. So here's the idea of cylindrical coordinates. Just take polar coordinates and take polar coordinates for the x and y, and take z for z. Okay. So right, this is x, y. This is x, y, z, and you have some point here, right? What you do is drop down to here. This point is x, y. So you have some point. Drop it down to the x, y plane, right? And take its polar coordinates. So take its polar coordinates, r theta, right? That is to say that if you drop, so here we project perpendicularly down onto the xy plane, and then you take its polar coordinates, so this is r and this is theta, right? And then you just use r, theta, and z to describe that. Okay, so instead of using xy for the first two coordinates, we use the polar coordinates, r and theta. Okay. So the map then going from is going to be r theta z turns into r cosine theta, r sine theta z. Right. So this is going from the cylindrical coordinates to the corresponding Cartesian coordinates. Right. Going from cylindrical to the corresponding Cartesian coordinates. R theta z turns into r cosine theta, r cosine sine z. Okay. So the point of using these coordinates is, of course, that that some things are easier to describe using these coordinates, right? So you know, of course, if you have a cylinder, right, you have a cylinder radius a and height, between heights h1 and h2. Right. So you have this cylinder floating in space here, right? And so the radius is a, and the height goes from h1 to h2. Right. This is maybe not so easy to. It's not that bad, but it's very easy to describe using cylindrical coordinates, right? This would be r goes from 0 to 2 pi, 0 to a, excuse me. Theta goes from 0 to 2 pi, and the z's range between h1 and h2. So this is, you know, the analog of a parallelepiped, right? The cylindrical, right? In you know, this, if you had something like this in Cartesian coordinates, it would be a parallelepiped, right? And here it's going to look like this. Okay, yeah.
Does r go from negative a to a or 0 to a?
From 0 to a. From 0 to a, because if we went from negative a to a, we'd actually cover the thing twice. And we'd basically get two copies of the guy, and when you did your integral, you get twice what you were expecting. You could, if you liked, you could go from negative a to a, but then you'd have to go. You got to go from 0 to pi, right? Yeah. Right, because that would give you just one copy. Yeah, that's fine. That would be fine actually. Okay. You know, similarly, so that's example 1, example 2, right? If you have r going from r1 to r2, theta going from, say, 0 to 2 pi, again, and z going from h1 to h2, then what kind of an object is described by this? Melissa? Okay.
It's like R is going from R1 to R2.
Yeah. So you've got a
Would
range.
be,
You've got a range of r's.
Like a cylinder with the cylinder cut out inside.
Yeah. So it's a cylinder minus a cylinder. And you have something like this, and you have another cylinder inside. You chop it off. Right? Another example. You have something like this cone. Suppose you have a cone, and the height is h, and the radius of the top is 8. So, can anyone tell me how I should describe this thing? Using cylindrical coordinates. You could do it like this. So, R goes from 0 to A, and theta is easy. Right? Theta goes from 0 to 2 pi. Right? We go all the way around. No matter where we are, we're going to go all the way around. Now Z is actually going to depend on something. It will depend on theta, not really. It will depend on R. If we're at R, then the Z's are going to range from something to up to H. Something up to H. What's this? It will depend on R.
It looks kind of like absolute value of R.
Okay, but let me make it. So A can be anything, right? So maybe I'll make it more like this to make it more suggestive. So A is. It depends on. You need to incorporate H and A into your descriptions. Right. What's the height? What's the height here? What's the slope of this line? Just H. H over A. Yeah. And so this height here is going to be. No.
I don't know.
Don't forget the H. H. Those of you who went through junior high school. Yeah. This is H. This is A. Right? If we are at this point R here, what's the height here? And the slope here is H over A, and we moved R steps over. So what's the height here? Thank you. Oh my God. Yeah, H over A. I'm sorry. I think this it could be some sort of like blockage because I didn't use X. Right? Maybe if I used X again,
Middle
prejudice.
school.
Yeah, prejudice towards X shows again. Right? Your knowledge is only phrased in terms of X. That's a little dangerous. It's true though, right? To some degree, yeah. A lot of what we learn is phrased. Everything is phrased in terms of X. A mistake, because that means that you're just understanding some sort of relations in terms of X, but not the idea, right? Because if you see this you say, oh yeah, right? The slope here is H over A, and so we move R units over, and so it should be H R over A. Right? But something stops you. Okay. So yeah. So here's the description, right? It's going to be like this. Right? Here's a cone. Here's a cone. Right? And it's pretty nice. So yeah, notice that what we were doing here is sort of like what we were doing in the previous section, right? You have the projection, basically, you have the projection onto the r theta axis, r theta plane. And here's the r theta plane down here. This thing describes the shadow, right? And then for each point in the shadow, right, the z's range from, the z's go for over some range from here to here. So the same sort of idea. Okay, so the question you should have at this point is, when you do the switch, when you do the change of variable, what factor do you need to correct the integral? So, what factor do we need to correct the integral this time? Right. You have your right. You have your you know, your triple integral over some object, and you'd like to rather express E in cylindrical coordinates, right? F evaluated at r cosine theta r sine theta z some factor, then dz dr d theta, is it? Right. Some factor dz dr d theta, or whatever. Right? It could be dr d theta dz, whatever. What do you think the factor is going to be? What do you think the factor is going to be? You might be able to guess it. 1 bonus point on the next exam to the person who guesses it. Peter. R. Yeah, why?
Well, I mean, the z is straight from Cartesian.
Yeah, the z is straight from Cartesian, right? So the only thing that you're doing, right, you can think of this in a couple ways, right? The things that you're integrating over are the same things that you're integrating before, but now you've just made them taller, right? You've just added some dz onto them, right? The d theta, dr are the same. The dr d theta are the same thing. What the area of this box, right? The volume of the box, right? Volume of the box is going to be r dr d theta, right? That's the area of the base times the height, right? dz. Right. So that's one way of thinking about it. Another way of thinking about it is to idea 1. Another way of thinking about it is to use the determinant, right? So you have we have this map r theta z was r cosine theta r sine theta. See? And the derivative, the derivative is going to be a 3×3 matrix. Differentiate with respect to differentiate this guy with respect to r with respect to theta, and then with respect to z. Differentiate this guy with respect to r, then with respect to theta, then with respect to z, and differentiate this guy with respect to r, with respect to theta, and with respect to z. Okay. And when you take the determinant of that derivative, what's called the Jacobian, it has a name, the Jacobian determinant. What do you get? You get, if you work it out, you get 1 times this thing, which is going to be r. Okay. So sorry to keep you over, but let me just do one example. So if f of x, y, x, y, f of x, y, z is, say, 1 plus x squared plus y squared, and we want to integrate over the previous cone. We want to integrate that thing over the cone. Well, the integral over the cone, let's call the cone C, is going to be this guy evaluated at r cosine theta, r sine theta, C, and then we need the r, and then whatever order we had, dr, d theta, dz, where r ranges from 0 to a, theta ranges from 0 to 2 pi, and z ranges from h over a r to h. And f of r cosine theta, r sine theta, z is, of course, 1 plus x squared plus y squared. So we end up with h 1 plus r squared r dz d theta dr. Okay. I think that should be enough for you guys to do the homework for this section. It's not like, it's basically this sort of stuff. So please do homework for 16.6 and 16.7 for Monday.